afternoon and welcome to Falling Walls Lab Australia 2021. I'm Anna Maria Arabia, Chief Executive of the Australian Academy of Science. I begin by acknowledging and paying respect to the Ngunnawal people, the traditional owners of the lands on which the Academy office is located. The Academy also acknowledges and pays respect to the elders, past, present and emerging, of all the lands on which the Academy operates and its fellows live and work. They hold the memories, traditions, cultures and hopes of Aboriginal and Torres Strait Islander peoples of Australia. The very first Falling Walls Lab in the world took place in Berlin in 2011, 10 years ago. It has grown from strength to strength. Since then, international labs have taken place in different cities right around the world. And last year, Falling Walls Labs took place in more than 90 countries. The Falling Walls Lab finale is held each year in Berlin on 9 November and marks the anniversary of the fall of the Berlin Wall. The finale gathers 100 winners derived from the international labs. This year, the 100 winners of the international labs will unite either virtually or in person. Each of them are finding solutions to the greatest challenges of our time and contributing to a better world. The top 10 global finalists will compete in the event called the Falling Walls Pitches, from which one presenter will be awarded winner in the Emerging Talents category. The winner will pitch their breakthrough project on the grand stage in front of a global audience of industry leaders, decision makers, investors, and international media representatives. The opportunity to participate on the global stage is up for grabs by the young researchers presenting at today's event. They were selected in heats held around Australian states. The Falling Walls Lab New South Wales was organised by the German Academy Exchange Service and EURAXESS. The Falling Walls Lab Queensland was organised by the University of Queensland. And the Falling Walls Lab Victoria was organised by Vesky with support from Deakin University. The Academy would like to acknowledge these partners for their support. Also making Falling Walls Lab Australia possible, we would like to thank the Falling Walls Lab Foundation, the Embassy of the Federal Republic of Germany, Canberra, and EURAXESS Researchers in Motion. Labs support interdisciplinary dialogue and international collaboration. They connect aspiring innovators and senior researchers, and they develop new and sustainable ways of scientific communication. Today, we're excited to hear from the 9 researchers and innovators from all disciplines who were selected to present their work, their business model, innovative project, social initiative or idea. We wish them the very best of luck. I would now like to hand over to our MC for today's event, Professor Hans Bachor. Hans is a Fellow of the Australian Academy of Science, and he is one of the driving forces of the labs in Australia. We thank you, Hans, for your passion and enthusiasm that continues to keep Falling Walls thriving here in Australia. Over to you, Hans.
Thank you, Anna Maria, and good afternoon all. I'm Professor Hans Bachor, Secretary for Education and Public Awareness from the Australian Academy of Science. I'll be your MC for this afternoon. As Anna Maria has mentioned once again, this year the lab is slightly different from those organized prior to the epidemic. In 2019, we met in the Shine Dome in person. Now we are scattered across many home offices, and we have you, our great audience. In this new format, we will show to you from across Australia great ideas for bringing down walls that limit us, here and everywhere. Today, we'll be selecting Team Australia for the global event in November. It is exciting for me to be here as your MC for this finale, and to see all of these researchers sharing their amazing work. Each presenter has just 3 minutes to make their case. to explain the wall they wish to break, and to show us what the solution is. We are most grateful to the panel of distinguished judges who will select the winners of today's competition. Each of them already has the most distinguished career. All of them are making so many contributions to our country, in science, in technology, in business. Full introduction would just blow you away. So let me introduce the jury members. And they are Dr. Cathy Foley, jury chair and Australia's chief scientist. Dr. Dan Grant, chief executive of MTP Connect. Ms. Kate Hart, ANZ Strategic Operations at AT Kearney, which is a management consultant company here in Australia, around the world. Ms. Rosie Hicks, CEO of Australian Research Data Commons. Professor Michael Schütz, Director of the Jemison Trauma Institute, Metro North Hospital and Health Service. Professor John Shine, President of the Australian Academy of Science. And last but not least, Dr. Jack Steele, Director of Science Impact and Policy at CSIRO. Falling Walls Lab brings together young scientists, engineers, professionals from across the globe to present their vision on how to make the world an even better place. Please let me introduce our presenters today from across Australia. They all have qualified for this finale. The presenters: Breaking the Wall of Unsustainable Healthcare, Elizabeth Austin from Macquarie University. Breaking the Wall of Toxic Cryopreservation, Saffron Bryant from RMIT University. Breaking the Wall of the Brain to Cure Brain Cancer, Lars Esser from CSIRO. Breaking the Wall of Waste to Energy, Arinze Ezieke from the University of Queensland. Breaking the Wall of Parkinson's Disease, Sara from the University of Queensland. Breaking the Wall of Stem Cell Therapies, Jiao Jiao Li from the University of Technology, Sydney. Breaking the Wall of Prostate Cancer Treatment Resistance, Chamikara Liyanage from Queensland University of Technology. Breaking the Wall of Alien Fish Invasion, a Trojan War, Lokman and Norazmi from the University of Tasmania. And Breaking the Wall of Access to Life-Saving Vaccines and Therapeutics, Anushi Kajapaksa from Murdoch's Children's Research Institute. We are looking forward to hearing from our presenters shortly, but first, to officially open the event, I would now like to welcome His Excellency Dr. Thomas Fitschen, Ambassador of the Federal Republic of Germany to Australia. Your Excellency, please.
Dear Falling Walls participants and presenters, distinguished members of the jury, a warm welcome to the 2021 Falling Walls Lab Australia. This competition was held for the first time in Australia in 2016, and since then it has become a flagship event of German-Australian cooperation. It's hosted annually by the Australian Academy of Science, and I would like to thank the Academy already now for once again partnering with us and for organizing the event. As all of us have been living in some form of lockdown, quarantine, or under restrictions of travel internationally and even domestically, it seems that the virus is putting up new walls where there were none before. This is also affecting research institutions, universities, companies large and small, and not least the Falling Walls competition. Contacts are being cut off or severed, conferences and meetings cannot take place. Sometimes, as we are experiencing in the ACT right now, you cannot even meet a colleague over coffee to discuss or share ideas. This runs counter to the very idea of Falling Walls, which from its inception was about connecting people, connecting scientists with business leaders, connecting industry with innovators, and also internationally connecting Australian talent with the German innovation scene. But here we are. For the second time already, the Canberra Falling Walls finale cannot be held live and in person, but only virtually, as we tend to call it. And yet, I'm delighted to note that this does not affect everyone's interest in Falling Walls. Your continued enthusiasm manifested again this year by a high number of submissions from young talent all across Australia, and the steady support given by the Academy of Science is proof that we can overcome the latest set of walls again, that we can come up with new forms of presenting and sharing innovation, good ideas, and your exciting project proposals. I'm convinced that by doing so, Falling Walls Lab Australia will also strengthen bilateral cooperation between Australia and Germany again, by identifying breakthrough science and innovation ideas from young Australian researchers that have the potential to break a wall and change the world again. It is of course a pity that once again I cannot promise the winner to go to Berlin for the World Finals. That was a great incentive before, and obviously there is no true compensation for not being in Berlin. But let me try nevertheless. I have the pleasure of announcing today that the German Embassy is awarding a cash prize of 1,000 Australian dollars for the top 3 scorers of today's Canberra Falling Walls Lab, and that means 1,000 each. It's financed by the Ministry for Education and Research, and I hope that may serve as an incentive for you this week. To conclude, I would like to congratulate all participants already now for being part of this year's Falling Walls Lab in Australia. And now I look forward to hearing what your breakthrough ideas and innovations are for 2021.
Thank you very much, Ambassador Fitschen, for your inspiring words. Now, please welcome Australia's Chief Scientist, Dr. Cathy Foley, to say a few words as today's jury chair. Over to you, Cathy.
Thanks, Hans, and hello, everyone. I'm speaking from the traditional lands of the Cammeraygal people in the northern part of Sydney, near Ku-ring-gai National Park, and I pay my respects to elders past, present, and emerging, and to any Indigenous people who are today. I pay my respects to you as well. It is so great to be part of the 2021 Falling Walls program, and it's one of the wonderful bonuses that comes my way through being Australia's Chief Scientist. Under lockdown and with travel restrictions, I haven't had the opportunity to go around and visit many of the labs firsthand to see the research that's happening around our country. But this event has been a way of making me feel a bit connected, so thank you very much. I'm very familiar with the Falling Walls program because I used to recommend participation of researchers from when I was at CSIRO. It's an opportunity to really develop the presentation and pitching skills that the modern researcher needs in their toolkit. Being able to explain the impact of your research is so powerful and absolutely necessary to be able to make sure that everyone understands what you're doing, but also to make the case of why your research should be supported. I want to give my congratulations to all the finalists. Getting here is a real achievement in itself, regardless of the outcome, and you should capitalise on this. I also want to thank the Ambassador of Germany for the very generous contribution he's making to this with the cash rewards for the top 3. That is a very special and exciting announcement. As my privilege to chair the judging panel and work with my colleagues, I know that selecting the winners is going to be really difficult, and I am confident, though, that my fellow judges' advice and knowledge and experience will really help us make the best selection. Even though this is an international engagement offered by Falling Walls to be something which normally would have travelled over to Germany, this time it's been moved online. And there are many opportunities, though, even though we are online, to make real connections using digital platforms, which is actually a fantastic outcome. And I saw this and the power of this recently when I was chairing the International Women in Physics Conference in July this year. We found that because we were online, we had an array of participants that were much broader from many different countries for the first time, where travel, time, and visa restrictions didn't play a barrier. So our finalists today, they're an example of amazing pipeline of researchers that we have and potential for research leaders attacking STEM to deliver breakthrough ways to push down the walls. And it's great to see just how they are making these walls fall. They are a preview to what we think, what I think is going to make Australia great and be something which will allow us to know our future is in good hands. So back to you, Hans.
Thank you, Cathy. We're off to a good start. We'll now proceed and start the presentations. We have a level playing field for all our 9 presenters. Each will have 3 minutes, followed by 2 minutes for questions or comments from the jury to the presenter. Our first, second, third place winners will be decided by the jury and announced at the end of this event today. In addition, People's Choice winner today. And this is over to you, our live stream audience. You are encouraged to vote for this winner. Following all 9 presentations, the voting will open. The link to vote will be on the Academy's webpage and in the comments section of this live stream on YouTube. Also, we encourage everyone to engage today, either by YouTube or Twitter. Our Twitter hashtag for today is #FallingWalls21, and you can tag @falling_walls and @science_academy. Now, let's get started. Here are the great ideas for the future. Please welcome our first presenter, Elizabeth Austin from Macquarie University.
What is unsustainable healthcare, and how might that affect you when you are sick? My name is Elizabeth Austin, and I'm a postdoctoral research fellow at the Australian Institute of Health Innovation at Macquarie University. And I'm breaking the wall of unsustainable healthcare. Healthcare systems exist to provide safe, timely, quality care. But we are seeing a surge in demand for services, along with shortages in resources, that is making it increasingly difficult for our healthcare services to provide the quality of care that we expect. Even before the pandemic, our hospital emergency departments were operating more and more often at full capacity. Our doctors and nurses changed the way they work, take shortcuts, use corridor spaces and social connections to make sure their patients receive the care they need. Workarounds like these create temporary system capacity, but they are not sustainable. This means that healthcare systems that rely on workarounds like these are unsustainable. I want to break down the wall of unsustainable healthcare. To do this, I use the cognitive work analysis framework to better understand care interactions, such as those between clinicians and technology and clinicians and patients. I spent over 260 hours in healthcare services observing how nurses, doctors, and professional staff perform their work. I made notes about the tasks they performed, the people and technology they interacted with, as well as how the physical space was used. I saw problems with how people interacted with technology, space constraints, and adaptive work patterns that created extra work or slowed work down for staff, helping to explain why it is that patients are waiting longer to be seen and taking longer to treat. My formative models reimagine how work is performed. My models show how administrative tasks could be automated or redistributed during periods of high service demand, how patient support roles or kiosks could be used to support patient care during the different phases of the patient journey. My models provide a platform for creative innovation, for thinking outside the box of how care is currently delivered and imagining how care could be delivered in the future by designing new processes, advancing technology, and creating physical spaces that make care safer for patients and less stressful for the doctors and nurses that care for them. These innovations will help our healthcare system to be resilient, to cope with the increasing and unpredictable demand, such as we've seen during COVID, and enhance the provision of safe and timely quality care. In doing this, I will break down the wall of unsustainable healthcare.
Thank you, Elizabeth. What a brilliant start. We now have 2 minutes for questions. Please welcome jury member Dr. Cathy Foley to ask Elizabeth a question.
Hi, Elizabeth. What a great presentation. Really enjoyed that. I just have a question about, have you actually had a chance to test your model on a pilot situation, or is it still in the formative stages?
That's a great question, Cathy. We collected the data to inform our descriptive models before COVID hit, and then COVID happened, and we haven't actually yet had a chance to go back in and check our models. But we have been working with, in the team is myself and some human factors experts, and so we've come up with some out-of-the-box ideas for how healthcare could be delivered without the sort of constraints that healthcare practitioners who work within the walls and with the current devices might have. But I would love to go back in and check in with them and present our ideas and be like, hey, is this something that might work for you in your work environment?
Oh, thank you.
Thank you.
So I think we've got Dan.
Not sure if you can hear me, Elizabeth. Thank you for your presentation. Maybe following on from your answer. So I'm not there yet. Can you hear me now, Elizabeth? Can you hear
Sorry,
me
Dan, I can't hear that question. Could you repeat it for me?
Can you hear me now? Thanks, Elizabeth. Sorry, there's a bit of a technical delay here. Maybe following on from your answer to Cathy's question, you know, if COVID has taught us anything, healthcare can be delivered remotely using a whole host of new technologies. How do your models specifically take into consideration the growing dependence on telehealth?
Good question. And you know what? COVID has really sort of driven huge advances in how we use technology. And it highlights how fast we can change and adapt. But we have to remember exactly what it is that the purpose of our healthcare services are, so that we're making sure that we're really addressing the goal of our healthcare services. And that is for emergency departments, for example, it's to provide safe and timely care. And so making sure that the technologies that we do use when we provide care, whether it's remote or face-to-face, making sure that they are still aligned with that functional purpose. And I'm hoping that as we evolve and continue to use these technologies, and as diverse groups use these technologies, we learn how to harness them and integrate them better into the system. Because at the moment, there's not necessarily integrated that well, and I think we can really improve how they integrate with our healthcare services.
Thank you.
Thank you, Elizabeth. Thank you, Joey. Now, please welcome from RMIT University.
Imagine lying in a hospital bed. A life support machine beeps beside your head and the acrid smell of antiseptic fills your nostrils. If you don't get a new heart in the next week, you'll die. The trouble is, with current technology, a compatible donor will have to die within 4 hours travel time of that hospital bed, or the heart will be thrown away. In fact, 60% of all donated hearts and lungs are discarded because of this tiny time window. And blood products like platelets can only be stored for 7 days. These limitations lead to the blood and organ shortages that we're all aware of. And it all comes down to storage, or a lack thereof. The answer is cryopreservation. Cryopreservation is the process of cooling biological samples down to very low temperatures so that they can be stored for a long time. Unfortunately, right now, cryopreservation is limited to a very small number of cell types and no organs at all, which is why that heart only has 4 hours to get to you. Unfortunately, you can't just throw a heart into liquid nitrogen, which is minus 196 degrees, and expect it to survive. This is largely due to freezing damage. Imagine jagged shards of crystal ice piercing through the cells. It's almost universally lethal. This is where cryoprotectants come in. Cryoprotectants suppress ice formation, which allows cells to be stored at these low temperatures. However, for the last 50 years, we've relied largely on the same two toxic cryoprotectants, and they just don't work for many cell types. My research is focused on expanding the number of potential cryoprotectants by literally thousands by exploring new biocompatible alternatives. This includes designer solvents like ionic liquids, which are salts that are liquid at room temperature, and sugar mixtures. Both salts and sugars suppress ice formation, and they're biocompatible. After all, cells use salts and sugars all the time. I've already successfully preserved several cell types using these new cryoprotectants, and now I'm trying to optimize this by trying different combinations and different concentrations. The stem cell therapy market is valued at $14.7 billion US, and the assisted reproductive technologies market is set to reach $45 billion in the next 4 years. Both of these rely on cryopreservation. New, non-toxic cryoprotectants will reduce the cost of these technologies, making them more accessible. Furthermore, new cryoprotectants may allow the storage of new cell types and maybe organs, which would save more than 900,000 lives per year in the US alone, as well as you, lying in that hospital bed. Thank you.
Thank you, Saffron. What a great idea. Now we have 2 minutes for question and answers. Please welcome jury member Rosie Higgs to ask Saffron a question.
Many thanks, Saffron. Well done. I'm keen to know more about the novelty of your work. If a commercial company invested $1 billion, could they also create a competitive cryoprotectant? What's the competitive advantage of this work?
Yeah, sure. Good question. So I feel like it largely comes from my multidisciplinary background. So we are actually submitting a patent soon, so I can't go too much into specifics. But my background is in physical chemistry, which allows me to bring specialist chemical knowledge to a field that is largely dominated by biologists. So there's like chemical design that goes into these, which I think makes them more novel than is usually seen in this sphere.
I look forward to it. I look forward to finding out more. Thank you.
Thank you. I think we have a little bit time. Can I switch to John Shine, please, to ask Saffron a question?
I'm not getting audio.
Sorry, I was on mute. I can't even deal with the technology. That's in an important area. And look, just probably a fairly naive question. I mean, cryopreservation of whole organisms usually raises lots of extra challenges when you're as opposed to cryopreserving single cells in culture or something. Do you make any comment about the challenges or the difference between, I suppose, perfusion versus diffusion in cryopreservation?
Yeah, absolutely. Really good question. So, as you said, one of the limitations to storing organs is that you need that cryoprotectant to get to deeper cell layers. Right now, the cryoprotectants we use, because they're toxic, if you put an organ into the cryoprotectant, the outer layers get all the toxic effects and the inner layers don't get any cryoprotectant. So the idea behind my design is that you could perfuse or diffuse, but because of the reduced toxicity, those outer layers aren't going to be killed by exposure. So the idea being you could incubate an organ for even hours in these new cryoprotectants, giving it time to penetrate to deeper layers without killing the outer layers. So that's the idea behind this.
Thank you very much.
No worries.
Thank you, Saffron, and thank you. Now, please welcome the presenter, Lars Esser from CSR.
Hi, my name is Lars, and my mission is to break the wall of the brain to cure brain cancers. Thanks to medical innovations, many cancers can be treated nowadays using surgery, radiotherapy, and especially chemotherapy drugs. Unfortunately, these treatments don't really work well for brain cancers. For example, the most common brain cancer, called glioblastoma, has only an average survival of 10 to 16 months. And only 1 out of 10 patients is alive for more than 5 years. These dismal figures are really caused by the location of this cancer, as located in our brains. This makes it almost impossible for a surgeon to fully remove it without causing a lot of damage. Moreover, the brain has a wall around it, called the blood-brain barrier, with very tight border crossings. And this way is quite similar to Berlin Wall. Although it has a good cause, as it protects the brain from all kinds of dangerous toxins. Unfortunately, this also means that most chemotherapies cannot pass this either. Therefore, this is a wall that needs to fall to enable us to cure brain cancers. But I have to note, we cannot let it fall permanently like the Berlin Wall, because then any toxin can go to the brain, so we have to be more careful. I've been developing 2 strategies to achieve this. First, I've developed these very tiny nanocarriers, that acts a little bit like a Trojan horse or like the Trabant car, in a way it can fool the border crossing and letting the drug pass. And I've had some good results so far. But wait, there's even a better method. I've been using an advanced and precise focused ultrasound system that together with so-called microbubbles open up this barrier for a few hours to let this nanocarrier pass. I've developed these nanocarriers such that they deliver drugs preferably to tumor cells and thus limit side effects. I've been using radioactive drugs as these are very effective in killing cancer cells, and I can also monitor them using an image system. So this really allows me to see if the drug is cooling the brain and can tailor the patient treatment to this. At the moment, I'm investigating the first generation of these nanocarriers using a brain cancer model that I have established. And hopefully we can move to clinical trials afterwards. The cool thing about this technology is also that you potentially can use it for other brain diseases like Alzheimer's or Parkinson's. Unfortunately, there's no guarantee of success in science, but hopefully we can find a magic bullet and offer a glimpse of hope to the sufferers of brain cancer. Thank you very much.
Thank you, Lars. Amazing opportunities again. Now we have 2 minutes for question and answers. Let's keep it within 2 and hopefully 2 questions. So let's please welcome jury member Kate Hart to ask Lars a question.
Sure. Thank you very much for a great presentation. Super interesting. So just trying to understand, so nanotechnology and application medicine has been around for a while. What's unique and breakthrough about your idea here so far as the use for brain cancer?
Thank you for the question. In my case, it's really the combination of different kind of things. So on the one hand, you have the nanoparticles, by themselves, they can't really easily go to the brain tumors. So by combining it with focused ultrasound is where you really have the novelty that we can deliver like gene therapy and other drugs that usually cannot be delivered by themselves with a nanoparticle to the brain tumor by taking advantage of the focused ultrasound.
But thank you.
And now let me please ask Dr. Jack Steele to ask the second question.
Lars, nice complex piece of research that you're doing. I'm assuming that you're doing this work in animal models. Is that correct? And what models are you actually using?
Thank you, Jack. So I'm using a model that has been established by Kumar Burkhofer. And the great thing about this model is that we use a patient-derived stem cell line from a brain cancer, and that we put it into an immunocompromised mice, and the tumors grow then slowly over time. The great thing about this model is that the blood-brain barrier is still intact. So it's a very realistic model. So nothing can get there except if we use focused ultrasound to open up the blood-brain barrier. So it hopefully will help with the translatability of this research.
As I say, a very complex piece of research you're doing. Well done.
Thank you, Jack.
Thank you, Lars, Jack, and Kate. And now I would like to move on to the next presenter. Our fourth presenter is Arinze Ezieke from the University of Queensland.
Hello, my name is Arinze Ezieke. Have you ever imagined a world where waste can be considered a resource? A world where all agricultural generated residues can be converted to valuable products? Yes, in my research world, all that you may see as waste, I see as a resource. Similar to most countries of the world, Australia's berry sector produces tons of tasty fruits that contribute significantly to our economy. However, about 20 to 30% of these fruits are rejected annually due to quality standards. Most of these fruit rejects end up in landfills or are left open in the farms, contributing to environmental degradation, by proxy posing a threat to the health of you and I. The farmers are burdened with the challenges of finding the best possible way to manage not just these fruit rejects, but other residues such as the coconut coir coming from the fruit cultivation. My research focuses on finding the best possible approach to sustainably harness this so-called waste into resources. Anaerobic digestion is the key technology in my research. This basically involves feeding a group of microorganisms with these fruit rejects, which in the absence of oxygen are converted to energy in form of gases. However, it's not that simple, considering that the acid contained in these fruits could affect the balance within the microbial community. Imagine a football team of 11 players with different responsibilities facing a tough opponent. For this team to win a match, the coach has to constantly tweak the formation so as to establish a balance amongst the players. I am the coach in this research. The microbial community are my players, while the fruits are the tough opponents. By tweaking the work within the microorganisms, a balance can be established within the community, which will be more simple and cost-effective than current practices that either utilizes a cost-intensive complex dual system that separates the microorganisms into two distinct communities, or by co-managing these fruits with certain ideal ways, such as the livestock manure, that might not be readily available in certain localities. By utilizing the approach proposed in this current research, maximum energy can be recovered from these fruit rejects. A further energy balance analysis confirms that a part of this energy can be used to run the anaerobic digester and return to the farm as a source of electricity and heat, while other parts can be used to power other systems for the management of other residues such as the coconut coir that would be difficult for the microorganisms to digest. The output from this other system will be nutrient-rich ash that can be returned to the anaerobic digester as a supplement for the microorganisms or returned to the farm as a soil conditioner for the crops. It is my belief that the outcome of this research would be a win-win situation for all stakeholders involved. Myself, as a researcher and coach of these microorganisms, the farmers that will see the farm become energy and nutrient self-sufficient, the climate that will experience less release of greenhouse gases, such as methane and carbon dioxide, and of course, the government that will see the waste management challenge of a key sector in our economy under control in a rather sustainable manner. Thank you.
Thank you, Arinze. What great opportunities in sustainability. So for the 2 minutes, I would like to welcome jury member Jack Steele to ask a question to Arinze.
Arinze, excited about the opportunities here. You were talking about food waste To what extent do you think this would be applicable across other sources of waste, like outcomes from fermentation arrangements in, agricultural, manufacturing, breweries, etc.? Or how specific is it to food?
Thank you, Dr. Jack, for this question. So yes, the beauty of what I have done is that it is not just limited to fruit waste only. So it cuts across most waste with the same or similar characteristics. And so if you have the food waste and you have other waste coming from, like you mentioned, fermentation process, these can be actually exploited and energy to be recovered from this kind of waste. So we are not limited to just the berry sector.
Okay, thank you.
Thank you. May I invite Cathy Foley to ask a quick second question and quick answer?
Okay, well, very quick question from me, Arinze. That was a lovely idea of a method of turning fruit waste into energy conversion. Can this be done in a compact way at the farm gate? So farmers could turn their leftovers or fruit that can't go to market and turn that into power that they can put onto the grid.
Sorry, Dr. Cathy, could you just highlight the first part of your question?
We're running a little bit into technology issues here. Yeah, so Arinze, the question was, could you have a compact machine that would produce power straight back into the grid on a farm?
Also, yes, the answer to that is yes. So basically, what the anaerobic digestion does is just to, our idea is to maximize energy production from this fruit waste. However, for you to convert these raw energy into electricity and heat, you need a cogeneration system, which can easily be sited on these farms. So when you have a cogeneration system on the farm, you can easily convert the raw energy coming from these anaerobic digester to electricity and heat, then distribute accordingly. Thank you.
Great, thank you very much, Anjini. And now let's move on and welcome our fifth presenter, Sara from the University of Queensland.
Imagine your life with tremor, stiffness, and pain, where simple daily activity like holding a glass of water feels like an achievement. The worldwide burden of Parkinson's disease has more than doubled over the past 26 years, from 2.6 million to 6.3 million by 2015. It is estimated that by 2040, it will reach 20 million people. This disease is the fastest growing neurological disorder worldwide and has reached pandemic proportion. It exerts enormous financial burden on our healthcare system. In Australia, 1 in every 300 people live with this disease. This disease can affect any one of us. Sadly, there is no cure for Parkinson's disease. In Parkinson's disease, as the person ages, there's gradual accumulation of protein aggregates in the brain, which activates the immune cells. This triggers inflammation and damages the nerve cells. Thus, a vicious cycle of chronic neuroinflammation sets in. Metaphorically, I would like to call it as brain on fire. So my approach is to halt this detrimental effect on neurons and help the victims of Parkinson's disease. My next question was, how do I cool this brain? In a groundbreaking recent research by our group and other leading neuroscientists, we have identified that a key protein called NLRP3 inflammasome enhances neuroinflammation. The results provide compelling evidence for NLRP3 activation in brain of Parkinson's disease patients. In my PhD, I am looking into new regulatory molecules in this pathway because this is critical in developing new treatments. Interestingly, using cellular and experimental models of Parkinson's disease, I have identified a key target that can stop neuroinflammation. My next step is to validate this target using genetically modified mice. The good news is that if the results from my target validation is positive, then modulating this new target could potentially be the next first-in-class treatment for Parkinson's disease. Thank you.
Thank you, Sara, for such an optimistic, positive outlook. Now, for the 2 minutes of question and answer, I would like to ask Professor John Shine to ask the first question.
Thanks very much, Hans. Thanks, Sara. It's great. It's certainly an important problem, a big challenge. The older I get, the more important this topic seems to become. So, look, you've obviously got a great target there. I suppose what must concern you, though, is its delivery. And have you got any evidence that you're actually, how you can inhibit, I think it's NLRP3, in the whole animal? I mean, knockout animal is one thing where it doesn't have it, but if you're getting a drug in there, have you got any evidence that in a whole animal, this compound will actually work or get through the blood-brain barrier, etc.?
Thank you, John, for the question. So I have identified a new target. We have not reached the step of developing the drug yet. So once we validate our target using genetically modified mice, it is after that we will move the project to the druggability of the target. And so we have not reached that stage yet.
Okay, yeah, the target at this point. Yeah.
Yes, correct.
Okay, thank you.
Thank you, Sara. And now for a second question, can we please switch to Rosie Hicks?
Thank you, Sara. Great presentation there. I love the idea of the brain on fire. A very important area, a lot of research. You have, I think, already touched on my question about the where to from here. But in turning this into a reality, can you tell us a little bit more about the next steps and perhaps how you would see collaborators being important?
Thank you for the question, Rosie. Currently we are having very exciting results with our mouse models of Parkinson's disease. So we have neurotoxin-based mouse models on which, by stereotactic surgery, we have identified that our target is highly upregulated. Which is very promising. And also in our laboratory experiments, we used neutralizing antibody, and we saw that there is a significant effect on inflammation. Mostly in my PhD, I'm doing the basic research of identifying and validating the target. So once this is identified and validated, we would be moving on for the drug discovery process, which is another 10 years of work. So, as your second question, with collaborators, we are already in touch with collaborators for this project, and we are potentially in future, we are looking forward as we are moving forward hindrances with the druggability or anything, and I think having collaborators with it would really help. And moving forward, we are looking forward to have more collaborators and probably pharmaceutical companies involved in it. Thank you.
All the best. Thanks a lot.
Thank you.
And Rosie, we're already past the 50% mark, and let me include our technical team. It was so much in an Iron Dome, but we're doing remarkably well, and we're trying to provide the same access to all of you presenters. So, please welcome our sixth presenter, Jiao Jiao Li, from the University of Technology, Sydney.
What if you could cook a magic soup to feed little magical creatures so they can produce a magic potion for curing a dreadful disease? I'm doing this with stem cells, magical creatures which, when grown in the right environment, can produce these tiny particles full of beneficial factors to act as a cure for devastating diseases such as osteoarthritis. Osteoarthritis gives you agonizing pain in the joints, from hips and knees to hands and ankles, preventing you from doing simple things like walking around or even just getting out of bed. And because of this reduced mobility, you're twice as likely to die from concurrent diseases like cardiovascular disease or diabetes. The bad news is that osteoarthritis has no cure. The doctor will give you drugs or ask you to do some exercises to make your joints less painful, but it does not stop the progression of disease. Ultimately, you can choose to have your joint removed to stop the pain and replace it with an artificial implant. However, this is not an option for older folks who cannot tolerate the risks of surgery, and for younger people, the surgery can have many complications like infection, and the implant only lasts a limited number of years. So what can we do? The good news is that we're working towards a cure for osteoarthritis by developing new ways to reduce inflammation and induce self-repair in joints. I'm working on a solution using stem cells, cells that have the ability to repair damage. These stem cells can be sourced from your body, like the bone marrow or fat, and have a remarkable ability to respond to the environment they live in. Through a pioneering approach at the interface of engineering and biology, I for the first time used computational methods to discover the best environment for growing stem cells. In response, they produce these tiny, nanoscale biological particles called extracellular vesicles, containing the most effective bioactive molecules for treating osteoarthritis. Once purified, these vesicles can be injected into your joint as a magic potion to help stop the pain and also disease progression. We're certainly already seeing very promising results when we apply these vesicles in the lab to disease cells from patients with osteoarthritis. This research could deliver us a new therapy that brings life-changing benefits to hundreds of millions of patients globally, including another 500 new cases of osteoarthritis by the end of this presentation, and reduce an enormous burden on our healthcare systems. And guess what? We can adapt the same workflow to develop new stem cell-based therapeutics for other diseases as well. Stay tuned.
Thank you, Jiao Jiao, for your inspiring ideas and opportunities that might open up. Now let's use our 2 minutes for questions, and I would like to welcome, do you remember Dr. Dan Grant, to ask Jiao Jiao a question?
There we go. I think we've got the technology working now. Thank you for that presentation. Really interesting work that you're doing and clearly addressing a huge unmet need. Can you tell us a little bit more about the types of stem cells you're using, and also whether or not the translation of this approach is using autologous or allogenic cells?
Yes, sure. So, very great question. Thank you. So the stem cells that we're using are what's called mesenchymal stem cells, or now the field prefers to call them mesenchymal stromal cells, and they're most commonly found in the adult bone marrow and fat, and they have an inherent ability to be anti-inflammatory and also pro-regenerative as well, which means they produce, for example, these amazing biological particles that contain a wealth of bioactive molecules. And the way that so currently the stem cell therapies that are out there are autologous, but with the ability to isolate these biological particles called extracellular vesicles, we're actually able to use them allogeneically, so using it from another patient, because the great thing about this is that what we call the extracellular vesicles actually have minimal immunogenic potential compared to the parent cells themselves, so, which actually opens up the possibility of deriving these vesicles from allogeneic cells and applying it as an off-the-shelf therapy.
Excellent, thank you for that.
I still go with the second. Thank you. So would I like to ask Professor Michael Schütz to ask a quick question, if that's possible? Mm.
You can't hear me? Okay.
Hello.
Okay.
Okay. Well,
No.
How does your proposed stem cell therapy differs from other ones which were tested but less effective, also for osteoarthritis? What is the superior aspect of your approach to others?
Sure. I would say the first aspect of this answer would be the fact that I'm using the extracellular vesicles instead of the stem cells themselves, because as you said, in osteoarthritis, people have been testing them in clinical therapies. Systematic reviews reveal that they are not very effective in the long term and results are inconsistent. So now people are going into, let's try different doses and frequencies, and it's really expensive and time consuming. So my preliminary research has actually revealed that these stem cells, because of their amazing ability to respond to the environment, when you put them into a disease environment, they respond to the disease environment as well. And by using the vesicles instead of the stem cells themselves, the vesicles contain the same anti-inflammatory and pro-regenerative functions of the stem cells instead of actually responding to the environment and taking on diseased phenotype. And the second part to this question is that I'm actually making these vesicles disease specific as well, which no one has done in the stem cell field or in the extracellular vesicle field for osteoarthritis, or probably for any other disease as well. And I'm using the machine learning approach, the computational platform, to optimize the growth conditions for the stem cells so that these vesicles can contain bioactive factors that are specific for the treatment of osteoarthritis. Thank you.
Okay, thanks.
Thank you, Jiao Jiao, and thank you both members of the jury. And let's try to be short with the answers, please. So please welcome our second presenter, Chamikara Liyanage from the Queensland University of Technology.
You can't hide yourself after committing a crime. However, cancer has been always smart to kill millions of people while hiding themselves from all our treatment regimens. This has been true for prostate cancer as well, the most common cancer in men in 112 countries. In Australia, 1 in every 6 men has the potential to be diagnosed with prostate cancer by the age of 85. But being diagnosed by prostate cancer is not a death warrant at all. Until the cancer remains only in your prostate, it can be treated with surgery or radiotherapy. But the deadliest aspect of prostate cancer is when cancer cells escape from the treatment to other body parts, such as bones, lungs, and liver. And there is no curative treatment available for these advanced prostate cancers, and the survival rate falls to less than 30%. By 2040, more than 700,000 deaths per year are estimated for men having advanced prostate cancers. For this reason, researchers are always searching for an effective treatment with better disease control and longer survival rates. To find an answer to this question, we looked deep inside the cancer cells, where nobody has ever looked on. We discovered a novel group of microproteins hiding inside cancer cells that might provide an answer to break the walls of cancer treatment resistance. Microproteins have been continuously ignored by researchers because of their small size. Surprisingly, microproteins are produced by genes which previously believed as non-coding genes that do not make any proteins. The key breakthrough of this research, it's not just the discovery of microproteins, it's all about their biological role. So we used a viral vector-based gene delivery method to reintroduce microprotein genes inside cancer cells and animal models while amplifying the number of microprotein copies. They have seen a significant reduction in cancer growth and their potential to invade other tissues, providing preclinical evidence on the cancer-inhibiting role of mycoproteins. Because of the high action potency of mycoproteins, their cancer-inhibiting activities are highly reproducible, and viral vectors have been modified to improve their stability, safety, and biocompatibility with human cells. In upcoming years, we propose to commercialize our products and set up clinical trials for the first ever mycoprotein gene therapy to prostate cancer patients. Combining mycoprotein gene therapy with existing cancer treatments, more than 80% of patients are expected to survive from the treatment resistance. Not only this improve the patient's quality of life, it will save billions of dollars from the prostate cancer patient management. Discovery of mycoproteins will not just shape up the legacy of conventional cancer treatment, it will open up new avenues in modern medical sciences. Nevertheless, mycoproteins are still the lilliputs in medical research, but never underestimate little things, because it's little things that make big things happen. Thank you.
Thank you, Chamikara. Now let's use our 2 minutes, and I would like to ask Professor Michael Chus to ask the first question of Chamikara.
Thanks, Chamikara. Very interesting aspect. Are there any potential side effects of the microprotein treatment on healthy cells? Is there anything you have to consider?
Thank you so much for that question. As of late 2020, more than 100 in vivo viral vector gene therapies are at clinical trials, and only 4 of them are in the market. And only one viral vector that has been successfully introduced into prostate cancer, and that is for the p53 tumor suppressor gene. But most of these gene therapy approaches face the critical issue of having limited package sizing to deliver target large genes. And they are, because of their large genes, they are less efficient in making proteins, and we have to introduce large doses that makes the therapy more cytotoxic, as well as more immunogenic, as well as more expensive. But being a small protein, the mycoprotein genes can be easily introduced into the viral vectors, and they have high action potency. They have a high biological activities inside cancer cells, so they're highly reproducible in using in gene therapy. And also, we require only small doses. Compared to previous times, we don't need to use large doses and in more times. So they create less side effects, as well as less immunogenic and more cost-effective for the patients as well.
Thanks.
Good. So could we have a quick second question and a quick answer, obviously, from jury member Dr. Jack Skeel?
Chamikara, I always feel uncomfortable sitting in my seat when this topic comes up, and I tend to move around a little bit. As you pointed out, this is a fairly common phenomenon in aging of men, but there's the question of whether to treat or not, depending on whether or not it's going to actually have a metastatic consequence. Is there any component of your research that's likely to give an immunoassay for whether or not you've got metastatic spread of prostate cancer?
Yeah, currently what we are trying to do is using animal models to see whether these microprotein gene therapy can be used to reduce the prostate tumor growth and their potential to invade other tissues, other body organs such as bones, lungs, and liver. And we're going to use a specific subtype for that, the castration resistant. That means hormone independent subtype of animal models in later stages. And we're going to introduce intraprostatic or subcutaneous viral vector gene therapies in these animal models, and seeing how they will be metastasizing to other tissues, particularly lungs and bones. And the current gold standard therapy used for prostate cancer is the hormone therapy. So we're going to introduce these microprotein gene therapy in combination with the hormone therapy to see how the metastasis can be reduced and improve the patient's quality of life.
Okay, many thanks.
Thank you, Chamikara, and to both of our members of the jury. Now, please welcome our 8th presenter, Lokman, Tasmania.
Sad truth. Australia has one of the highest extinction rates in the world, where the #1 threat for Australia's unique biodiversity is the invasion of alien species. Recently, it was reported that invasive species cost us around $24.5 billion a year. And ladies and gentlemen, this is just an underestimated value. One of the alien culprit is Gambusia holbrooki, aka the mosquito fish, which aggressively invading our freshwater ecosystem. This species is listed as the top 8 worst aquatic species globally. This small fish threaten more than 30 native frogs, fishes, and even aquatic birds, including endangered species such as the green and golden bell frog. They are bullies in the aquatic ecosystem where they compete for food, they interfere with reproduction, and attack fish and tadpoles, causing population depletion of native species. Now, physical and chemical solutions to eradicate these alien pests have been unsuccessful and to a certain extent have negative impacts on native species. For example, yes, we can use poison. We might kill Gambusia, but also accidentally kill other native species. Therefore, a genetic solution centered on Trojan chromosome carriers was identified as the most feasible strategy to combat this pest at continental scales. Now, this is the first time this concept or strategy is being tried in Australia. There are other genetic approaches, but they are exploratory compared to this approach. The theory here is to produce and release physically female fish with male genetics produced via hormone sex reversal into the wild. They'll then breed with normal males, which will then lead to a male-biased population. And when there's too many male, the population will decline and collapse, thus eradicating this pest specifically without harming native species. This approach will complement other genetic approach that might be developed later as the technology advances, and it can also be applied to other alien invasive species such as carps. Currently, I've overcome significant walls to implement this war strategy, which include understanding its basic biology, development of Trojan females, and assessment of its reproductive fitness. We are now ready to enter the next phase, upscaling to pond trial. Though it might still need a bit of time, it is clear that we are on the right path to win this war. Thank you.
Thank you, Lokman, for your enthusiastic presentation. For the 2 minutes of question and answers, please let me start with Professor John Shine to ask the question.
Yeah. Thanks, Hans. Thanks, Lokman. That's fascinating talk in a really interesting area. I can see how introduction of the sort of Trojan female would give rise to a pretty rapid drop in the population numbers. But is that sort of self-limiting? Because there'll still be normal females there, and they'll be able to produce some normal females. I mean, you won't actually eradicate it, will you? You'll just keep the population down, or am I missing something in that?
Oh, thank you, John. That is actually a very good question. So in this approach, we actually need from time to time to add more stocks of the Trojan females. So from time to time, as we stock more fish, we also need to look at the genotype, the population dynamic of the fish at that time. So currently, based on our current model and based on our tests in the lab, we can see that by adding more fish and by controlling and observing the genotype, the population dynamics of the fish, we can, at the end of our trial, to actually produce this male biased population.
Very good, thank you.
Now, for a second question, let me quickly switch over to Kate Hart.
Hi, Lokman. Thank you for a very interesting presentation. So we've obviously got a little bit of a checkered history so far as the introduction of various alien species to control population.
Yes.
You know, what's going to be different here, and how are the risks of a alien introduction being managed, both within crossbreeding or other impacts within the biodiversity?
Yes, that is actually a very good question. Thank you, Kate. So basically, one of the I guess the best benefit for this technique is actually it is reversible. So let's in case, let's say, anything happen, okay, we can actually just stop stocking the fish, and then let the condition be back to normal prior to addition of more Trojan females.
All right, that makes sense. Thank you.
Thank you.
Good. Thank you. And now we are moving on to presentation. The final 9th presentation will be Anushi Kajapaksa.
The thought of a needle might make you cringe, but not everyone has the privilege to enjoy the life-saving benefits of vaccines and therapies that are available today. In fact, last year alone, 23 million children did not have access to basic vaccines and therapies that could protect them from major respiratory illnesses. A major contributor, RSV, or the really serious virus, not kidding, the respiratory syncytial virus is now identified as the leading cause of pneumonia in children under the age of 5. In Australia, children experience around 2 to 7 episodes every year, costing the Australian economy 24 to 50 million Australian dollars. A recent report from the Time magazine showed that there was a spike of around 2,000 cases in one single week in the United States. So here comes the war. Currently, we do not have vaccines or therapies approved for RSV. The only protection offered by a monoclonal antibody is not only expensive, it's not accessible to children who need it the most. So we need improved strategies, potentially low-cost, simpler approaches to deliver vaccines and therapies to the children who need it the most. One approach may be to deliver vaccines and therapeutics directly to the lungs to provide a strong frontline defense system. The lungs offer a large surface area for absorption, and importantly, it's a non-invasive route, but it gives you access to the immune system. It's actually a simple approach that can be applied in community settings and even in neonatal intensive care units. We believe one way to outsmart the viruses would be to shut the door at the point of entry, which is your lungs. Our patented solution involves a novel acoustic nebulizer based on electromechanical engineering. We use high-frequency sound waves to interact with the biomolecules to break up the surface tension in a very gentle manner. This allows us the efficiency to target the deep lung. By adapting microchips that's found in your mobile phones, we've been able to develop an inexpensive solution. I have led extensive series of preclinical trials involving laboratory work, involving a biologically relevant animal model to show that we can deliver complex biomolecules such as monoclonal antibodies to the lungs in real time. We are now ready to test if we could provide effective solution in a clinical setting. But we need to act fast and we need to act now, as by the time I would have finished this talk, 5 children would have lost their life to pneumonia caused by RSV. Although our focus has been on RSV, for which there is a dire need, our solution can be broadly applied across other respiratory diseases. So by inhaling for protection, we believe we could finally knock off the wall of life-saving vaccine and therapeutic access. Thank you.
Thank you, Anushi, for this final presentation. And now we have our 2 minutes for question and answers. I'd like to welcome back Dr. Cathy Foley to ask the first question of Anushi.
Hi, Anushi, that was a great presentation, a really interesting topic. Just want to understand a little bit more about how, whether the acoustic nebulizer actually interacts with the monoclonal antibodies, or are they separate? I didn't quite get that.
Thank you, Cathy, for that question. So as I understood it, how the biomolecule, in the case of monoclonal antibodies, interacts with the ultrasound waves is the question. So in our case, we use high-frequency sound waves, and it basically travels through the liquid interface and forms what's called a capillary wave. And basically that's what breaks up the surface tension in liquids. In the case of a monoclonal antibody, it's dispersed in, for example, saline, and basically it's the aerosol that forms as a result of breakup of the surface tension containing the biomolecule, in this case, the monoclonal antibody. So there is a direct interaction, and in the case of high-frequency sound waves, we believe that interaction is very fast, so there's not enough time to stretch or cause issues in terms of shear. So that's why we are able to deliver a drug that's actually safe and biologically active.
Thank you. That made a lot of sense. Thank you very much.
Thank you.
Thank you. And let's please switch over to jury member Dr. Dan Grant to ask the second question.
Thanks, Anushi. I enjoyed your presentation, and I have little doubt that RSV will become more of a challenge, particularly as we're spending more time in lockdown in the pandemic. You mentioned that you're working on a biologically relevant animal model. Can you tell us more about that and whether or not it really is sufficient to predict clinical outcomes?
Thank you so much, Dan. That's an excellent question. So the biologically relevant large animal model that we're working on at the moment is a sheep or a lamb model. And interestingly, lamb's immune system parallels that of human babies and human children. And their physiology and their human structure and anatomy is very much similar to that of humans and human babies, in this case. So in terms of translatability, we think it's a very unique model, especially because we've done, I've actually conducted an RSV challenge model, and they're able to mimic the disease quite well in terms of viral shedding and clinical symptoms. In our case, in particular, we've actually used a model where we house the mother ewe with the baby lamb, and in that case, we find that the symptoms are not that severe. Because unlike human babies where the babies are protected in terms of antibodies, the lambs are able to provide maternal antibodies. So there are some very subtle differences. There are ways to manage that. But I think in terms of clinical usability, it's an excellent model. Thank you.
Thank you.
Anushi, and thank you all jury members for your question. Presentation of question and answers. What a wonderful job you did altogether. What a wealth of ideas and possibilities. Now, the jury will get to work and will deliberate for 20 minutes. And then we'll be back to announce the top 3 winners, and they will have the opportunity to pitch videos shared on Falling Walls social platforms and potentially be selected as one of the 10 finalists who will take part in the International Digital Falling Walls event in November in Berlin. Now you can also vote from the public. The People's Choice voting is now open, so you can now cast your vote. Please note this is a different corrected QR code. So if you have voted earlier, please use this new QR code, and you see it on the screen, to vote again. Voting is open for 15 minutes only. So we will be back soon. We'll show you material and ideas from the Berlin events, but in the meantime, enjoy this fascinating science. We'll be back soon.
This is a South African beach daisy. To be precise, this is how it looks in Australia, where it's considered a common coastal weed. It was introduced here in the 1930s and in less than 100 years has taken on a rather new form.
The leaves are different, the way the stems grow is different, the flowers are different. Everything about them is different.
Professor Angela Moles wanted to be sure this was a case of rapid evolution. Her team tracked down the parent population in South Africa, collecting seeds to grow alongside Australian-sourced seeds in a rooftop glasshouse at UNSW Sydney.
Now the seeds were made in different conditions, right, because they were grown in different countries. So we did another year of work just growing them through one generation in the glasshouse to take out the effects of that maternal environment.
She describes the result as astonishing.
I thought we might see a few changes, but I wasn't expecting anything like that scale. It shows that these plants are capable of changing much more quickly than we realised at first.
The team even forced the two to cross-pollinate, but that resulted in relatively low germination. So if the plants were growing next to each other in the wild, Professor Moles thinks they would drift apart into separate species. Understanding how plants evolve has become her lifelong obsession. So much so, she once embarked on an ambitious global expedition collecting data from 75 different ecosystems.
There were deserts, there were rainforests, there was, shrublands and savannas, everything everywhere. In each of these places, I studied how much the plants were getting eaten by animals. So this could be by mammals or by little insects and things.
And that matters because of a long-held assumption that interaction with animals was a key reason for greater diversity of plant species in the tropics.
I found that plants aren't any more likely to get eaten by things if they grow in the tropics. And we'd also assumed that plants had stronger chemical and physical defences against the animals if they lived in the tropics. And that turned out not to be true either.
One thing is true. As the global climate changes, plant species are migrating and evolving to suit new conditions. But even with this, things aren't straightforward.
Interestingly, different plant species are moving at different speeds, and they're not all going in the direction you'd expect. So you'd expect plants to be moving uphill or to the south where it's cooler, but about 15% of the species that we look at in both studies are moving in the opposite direction, and we don't really know why.
But unanswered questions never deter Angela Moles. She's proud to be recognised as a leading woman in science with the Nancy Millers Medal.
It has been a difficult time to maintain my research momentum as my kids were young. It's so nice to receive this award.
We're looking at the brink of a quantum materials revolution.
It's about what science can do and what society can become.
Falling walls. What a great image.
Overall, I think it's a huge message of hope.
It's a unique event of that kind.
That's really exciting.
Oh, wow. Thank you.
Oh my God!
This is real?
I really enjoy putting my ideas into what's possible in terms of innovation.
Plastic recycling and efficient solar storage. They're two of the world's biggest challenges. Thomas Maschmeyer decided to tackle both.
One of the ways I approach my science is to look at a problem that really irks me. It's there, and I'm a scientist, technologist, so can I do something about it?
His solution to plastic waste is known as the catalytic hydrothermal reactor. It uses water at supercritical temperatures to convert end-of-life mixed plastics into recycled oil. Yes, oil. Nature takes millions of years to create oil, Professor Maschmeyer's reactor can do it in less than 30 minutes using materials that are currently clogging landfill and polluting our waterways.
And if we don't do anything different by 2050, we will have more plastic in the ocean than fish, and that's just not acceptable. So it's really about changing the conversation, making the problem of plastic into an opportunity.
The world uses around 100 million barrels of fossil oil every day, so his reactor technology could help power a circular economy. The process has been successfully trialled on the central coast of New South Wales and is now set to be rolled out commercially by Licella Holdings, a company he co-founded 13 years ago.
So the plants pay themselves after 4 years, and they should run for a minimum of 20.
Professor Maschmeyer's work on energy storage is equally game-changing. Research conducted by his team at the University of Sydney has translated into a new form of solar energy battery. And unlike lithium-ion, it doesn't overheat.
Our battery is completely different. It's a zinc-bromine chemistry, which loves the heat. We perform best at 45 degrees, where everything else dies. And we love going to zero state of charge.
That makes it perfect for harsh mining or agricultural settings or anywhere off the grid.
The appetite for solar battery solutions in those areas is huge, and the world's really waiting for that to replace the dirty and expensive diesel gensets in terms of running them over a 10-year period, to replace them with a no liquid fuel kind of situation, just solar panels and batteries. Huge appetite.
Professor Maschmeyer hopes his technology will assist the switch to a battery-powered world.
I love technology translation, and the latter half of my career has been dedicated to that, to really attack some of the big, challenging physical problems of our planet.
And that work has seen Professor Maschmeyer awarded the David Craig Medal, which recognises outstanding contributions to chemistry.
Can we change the world in 3 minutes? 3 young Australian researchers will try to do just that at the Falling Walls Lab finale in Berlin, an international forum for the next generation of outstanding thinkers and innovators. They will each present a 3-minute pitch alongside 100 other finalists from more than 55 labs across the globe.
It's very exciting, it's an amazing opportunity. I will be able to talk to different people, so potentially there might be a company that's interested in commercializing the platform.
Dr. Elena Schneider-Fuschig has developed a platform that measures drug concentrations in cystic fibrosis patients to evaluate and predict patient outcomes.
So patients currently only have life expectancies of about 40 years, which is not good enough just yet. So we still need to work on giving them longer life expectancies and helping them live better lives.
Kate Seacombe is investigating the gut microbiome's role in personalising cancer treatments to prevent intestinal toxicity, which can have a debilitating effect on a patient's quality of life.
Being able to predict gut toxicity from a range of cancer treatments is going to save money, it's going to save people's embarrassment, save pain, just really be able to increase people's quality of life during cancer treatment.
Rhys Piri has developed a chemical recycling process to take waste glass, which is currently going to landfill, and turn it into everyday products like fertilisers, detergents, and even toothpaste.
One of the things I like to say is we don't have a waste problem, we have a lack of incentive to recycle. So if we can increase the value of the waste products that we're trying to recycle, then it provides that incentive to actually use it in useful products.
From the side effects of medical treatments to a global waste problem, which of these walls will fall next?
The Australian Academy of Science, because questions need answers.
Out in the bush, catching and studying Tama wallabies still thrills Professor Marilyn Renfrey after 5 decades of research.
I'm passionately Australian and I really wanted to work on something Australian. But when I started honours, I said to my prospective supervisors, I want to do biochemistry and fieldwork. And they laughed at me. Well, I'm really still doing biochemistry and fieldwork.
She's also now a world expert on Australian marsupials and has pioneered research on the reproduction, development and conservation of some of our most iconic creatures, including koalas, kangaroos, wallabies and echidnas.
We use marsupials as biomedical models. They're mammals like we are, but they do some aspects of their reproduction a little differently. And that difference makes it easy for us to ask questions that relate to reproduction in mammals and even reproduction in humans.
The biggest difference is that marsupials give birth to an undeveloped baby that immediately crawls into their mother's pouch and continues to develop for a couple of months.
You can just open the pouch and look and see what's happening at stages which in us would be 6 to 8 weeks in utero. We're trying to understand the role of the hormones and the genes, how the genes and the hormones interact, particularly to control sex differentiations.
Professor Renfree's groundbreaking research is also important for conservation and management of these unique creatures.
I'd like people to understand that we are sitting on a biological goldmine in this country, and we really need to put more time and effort and money into conserving these special animals and doing research on them, because Australia has the distinction of having the worst record for extinctions of any developed country, and that's not a record that you want to be proud of.
Professor Renfree is being honoured with one of the highest awards of the Australian Academy of Science, the Macfarlane-Burnet Medal and Lecture. The sun is a major source of energy, and solar power is essential to a cleaner and greener future.
Well, my vision is, ever since we started the plastic solar cell project, that we would be using the sun as our major energy source, not just electricity, but also in manufacturing. It's not only a dream, it's essential.
Professor Andrew Holmes is a polymer chemist who has spent his life researching and building new molecules and materials. By modifying molecules, he's helped create new plastics and polymers, including flexible solar panels.
Printed plastic solar technology, I think, is certainly going to be a technology in the marketplace. There are some products already emerging. It has the advantage that it's lightweight, and it's flexible, and in principle it's significantly cheaper than the silicon solar cell technology.
It was Professor Holmes's groundbreaking work on light-emitting polymers that helped shape solar technology. His research was also vital to the emerging field of flexible electronics seen in OLED flat-screen TVs.
I would say the most exciting thing that happened was the unexpected discovery that plastic, ordinary plastic, that we used to wrap around electrical cables as an insulator, could actually behave as a semiconductor. And what's more, gave out light when it was sandwiched between two metal conducting electrodes and hooked up to a battery.
Like many of the world's greatest accidental scientific discoveries, it opened up a multitude of new opportunities and research paths.
We didn't know at the time how significant the consequences were going to be.
Professor Holmes says science discovery is essential, and it's important that applied research leads to commercialisation and useful applications.
The discovery of light-emitting polymers was a complete accident. We'd never written that research project that we were going to discover light-emitting polymers and even plastic solar cells, because we simply didn't know that that possibility existed. That's the excitement of science. Serendipity is hugely important.
For his remarkable contributions to science, Professor Holmes, former president of the Australian Academy of Science, is receiving the Matthew Flinders Medal and Lecture Lifetime Achievement Award. Symmetry is all around us, from giant spiral galaxies to tiny shells on the beach.
I'm really passionate about the mathematics of symmetry. Mathematically, we measure the symmetry by groups, and I use very deep theory and a lot of sophisticated computation to help me in describing the structures.
Professor Cheryl Prager pursued her passion for maths at Oxford University, where she received a scholarship to do a doctorate. It was there that she was introduced to the mathematics of symmetry, which has captivated her ever since.
A few years after I finished my doctorate, there was a massive theorem completed, the classification of the building blocks of all finite groups. This had been going on for about 50 or 60 years, and I was interested in understanding what the consequences would be to working out how to describe symmetrical structures. What would be the consequences for permutation groups, for structures? And this took a long time. It was not at all clear, and it was very exciting and also quite controversial in the time.
Now an internationally renowned mathematician, Professor Prager's 4 decades of research has had widespread impact. From digital communication systems to internet search engines, her algorithms are used worldwide.
These networks are the sort of mathematical structures that underpin the way we store data, the way we communicate, and finding beautiful symmetrical examples is of great interest.
The recipient of the Prime Minister's Prize for Science in 2019, Professor Prager is a trailblazer for women in STEM and a role model to many. In recognition of her incredible achievements, she is receiving one of the Australian Academy of Science's highest honours, the inaugural Ruby Payne-Scott Medal and Lecture.
I love a challenge, and science is a particularly important way of understanding the world. Science helps us really understand structure in the world, and mathematics underpins all of science.
To feed the world in 30 years' time, we'll need twice as much food as we need now. So how can we produce more effective, sustainable food crops? Professor Susanna von Kammerer is one of the world's leading photosynthesis researchers working to solve such problems.
My research area concerns mathematical modelling of photosynthesis.
Her team's research from 40 years ago changed the way photosynthesis was studied forever.
One of my first discoveries that thrilled me concerned the enzyme Rubisco. It's the primary CO2 fixing enzyme in photosynthesis.
Rubisco is the most abundant protein on Earth. Previously, scientists couldn't explain why there was so much of it.
How Rubisco operates is really one of the most defining characteristics of how CO2 is fixed by plants. Understanding its kinetics and so on has driven quite a lot of my research.
Professor von Kammerer continued to break new ground as she pioneered technologies and experimental techniques. Her research is used to predict global photosynthesis levels and to improve crop production across the world. But Professor von Kammerer wasn't always going to study plants.
It was sort of accidental. I had finished my honours degree in pure mathematics and I got a job as a lab technician here at the Research School of Biology.
The work was so captivating that she completed her PhD in the area, and the rest is history. She is now Deputy Director of the ARC Centre of Excellence for Translational Photosynthesis and leads an international collaboration on improving photosynthesis.
It's never boring, it's always varied. Like I started as a pure mathematician, I had no idea of practical experimental science. I learned that during my PhD, when I went from biophysics to molecular biology, new things. Constantly engaged in making new things, learning new things.
To celebrate her contribution to science, Professor von Kammerer has been awarded the inaugural Susan Corey Medal.
I'm really thrilled. I've admired Suzanne Corey very much. And I'm also very thrilled that we have an award for plant science.
It's this incredible connection of people, and I find myself just going, wow.
It's about what science can do and what society can become.
What was science fiction has now become science.
Falling walls. What a great image.
These robots are a human-made system, and so we're going to need to work together.
In future, we can do better, and we must.
Science always builds bridges, and I'm very proud to be part of it.
It's a unique event of that kind.
Speakers that take us to the edge of our understanding.
Bang. Great. So trying to think that this was the beginning of time makes no sense at all.
I'm going to show you the audience tonight.
Will you help me shine a light on this incredibly urgent issue?
This conference is all about getting walls to break down so that we don't damage humanity.
The fundamental question is, are we alone?
Breaking the wall means opening new windows and discovering the unexpected. That can be fantastic.
Yeah, wow, isn't that wow? The signal of two black holes coalescing. This is what it sounds like.
Through your commitment and your effort, you will create a better future.
It's time to act. It's urgent. Do it now.
I have not seen anything else like that worldwide.
I really enjoy putting my ideas into relation to what's possible in terms of innovation.
It's such a great opportunity for innovators to share ideas with people who can actually make them happen.
We can design a Spider-Man suit. It's not impossible.
This is a rapid-fire boot camp for young scientists from the entire world.
Falling Walls Venture shows that the excellence of basic research can turn into proud entrepreneurial solutions.
A rich diversity of science communicators across the world doing amazing things.
Falling Walls has pulled together an international group of luminaries. For me, is really a dream come true.
Community that cares.
Here I get new perspectives.
That was really inspiring.
Brilliant researchers. It's such an incredible atmosphere.
I've been learning a lot of interesting things.
Overall, I think it's a huge message of hope that you get.
There are walls everywhere. Let's bring them down.
It's a smelly hitchhiker that poses a major threat to Australia's farmers.
It's knocking on our door. It's turning up in container ships all the time, and it would be devastating to Australia's agriculture.
It's known as the brown marmorated stink bug, and although it looks similar to Australia's native stink bug species, we've so far been able to keep it out.
Often when an invasive species comes into a country, it doesn't have its native enemies. It's a kid in a lolly shop, you know, it takes off and it can explode, and then it's extremely hard to control.
The bug is a voracious eater. Look at what it does to apples, but it also feeds on corn, figs, grapes, peaches, soybeans, in fact more than 300 agricultural and ornamental plant species. The Australian government is so worried about it, the Department of Agriculture website says the species threatens our way of life. They've heightened biosecurity measures for goods imported from East Asia, Europe and North America. But the brown marmorated stink bug isn't the only threat to Australian agriculture.
There are pests knocking at our door all the time.
That's a key reason scientists spend so much time identifying species, both native and exotic. That information is then used by border authorities to keep Australia protected.
The Australian Academy of Science, because questions need answers.
Exoplanets are worlds that revolve around other stars, just like Earth revolves around the Sun. Thousands have now been confirmed, but there could still be tens of billions undiscovered. Exoplanets are hard to see directly as they're far away from us and outshone by the stars they orbit. But astronomers have developed ways to spot them, including the transit method.
It's where the planet comes between us and that star. It blocks a tiny little bit of the starlight, so the star gets a little dimmer, and then it passes on by and the star resumes its brightness. Now, if you see that happen every 45 days, then you've got a planet that's orbiting around a star with a year that lasts 45 days or 90 days or whatever the amount of time you've had to wait.
Another common way to detect exoplanets is the wobble or radial velocity method. This is where scientists measure a star's change in speed as it wobbles under the gravity of its exoplanets.
As that star is being swung towards us by the gravity of the planet orbiting, we are seeing its color shift ever so slightly bluer, and then as it moves away from us, it's going a little bit redder.
Many exoplanets could be just like Earth with a similar size and residing in the so-called habitable zone of their star, sometimes referred to as the Goldilocks zone because conditions need to be neither too hot nor too cold for liquid water. But being in the zone doesn't guarantee habitability.
Well, we look at Venus, and it's our size, it's a similar distance, habitable zone. That would be a really exciting discovery if we saw it around another star. But we know that Venus is a hellish world. It's the hottest planet in our solar system. It has a global warming effect that has just now run away to apocalyptic levels. There's no life on the surface.
Scientists say there's still a lot more to learn about these exoplanets, including their surface conditions, before they can determine if these alien worlds can support life.
The Australian Academy of Science, because questions need answers.
This is a South African beach daisy. To be precise, this is how it looks in Australia, where it's considered a common coastal weed. It was introduced here in the 1930s and in less than 100 years has taken on a rather new form.
The leaves are different, the way the stems grow is different, the flowers are different, everything about them is different.
Professor Angela Moles wanted to be sure this was a case of rapid evolution. Her team tracked down the parent population in South Africa, collecting seeds to grow alongside Australian-sourced seeds in a rooftop glasshouse at UNSW Sydney.
Now the seeds were made in different conditions, right, because they were grown in different countries. So we did another year of work just growing them through one generation in the glasshouse to take out the effects of that maternal environment.
She describes the result as astonishing.
I thought we might see a few changes, but I wasn't expecting anything like that scale. It shows that these plants are capable of changing much more quickly than we realised at first.
The team even forced the two to cross-pollinate, but that resulted in relatively low germination. So if the plants were growing next to each other in the wild, Professor Moles thinks they would drift apart into separate species. Understanding how plants evolve has become her lifelong obsession. So much so, she once embarked on an ambitious global expedition collecting data from 75 different ecosystems.
There were deserts, there were rainforests, there was, shrublands and savannas, everything everywhere. In each of these places, I studied how much the plants were getting eaten by animals. So this could be by mammals or by little insects and things.
And that matters because of a long-held assumption that interaction with animals was a key reason for greater diversity of plant species in the tropics.
I found that plants aren't any more likely to get eaten by things if they grow in the tropics. And we'd also assumed that plants had stronger chemical and physical defences against the animals if they lived in the tropics. And that turned out not to be true either.
One thing is true. As the global climate changes, plant species are migrating and evolving to suit new conditions. But even with this, things aren't straightforward.
Interestingly, different plant species are moving at different speeds, and they're not all going in the direction you'd expect. So you'd expect plants to be moving uphill or to the south, where it's cooler. But about 15% of the species that we look at in both studies are moving in the opposite direction, and we don't really know why.
But unanswered questions never deter Angela Moles. She's proud to be recognised as a leading woman in science with the Nancy Miller's Medal.
It has been a difficult time to maintain my research momentum as my kids were young. It's so nice to receive this award.
Good afternoon and welcome back from the break. I'm John Shine, President of the Australian Academy of Science, and I'm delighted to be here today as part of the jury. We'll soon hear from the jury chair, Dr. Cathy Foley, but before we do, I'd really like to acknowledge the time and the energy that the jury members have given for this event. Thank you therefore to my colleagues today, Cathy Foley, Dan Grant, Kate Hart, Rosie Hicks, Michael Schutz and Jack Steele. We sincerely appreciate your support of the event and we look forward to hearing the verdict very shortly. As Anna Maria mentioned, Falling Walls Labs support interdisciplinary dialogue and international cooperation. They connect aspiring innovators and senior researchers, and they develop new and sustainable ways of scientific communication. So important today as we face the global challenges of the current pandemic, climate change, environmental degradation, and a rapidly expanding population. And we are very grateful to the partners who enable these opportunities here in Australia. In particular, I would like to thank the German Embassy for being a trusted partner in this Academy event for the past 6 years and for generously providing the financial support. I also thank EURAXESS for supporting the lab for the second year in a row and for providing high-quality online science communication training to each of the 3 winners. We trust that this will be a long-term partnership. So now, to speak on behalf of EURAXESS, please welcome Nishat Shandilya.
Good afternoon, all of you. First of all, congratulations to all the finalists of the Falling Walls Lab Australia competition and to all the participants across the state heats who endeavoured to submit their breaking the wall ideas. These are unique circumstances, and hence your efforts of presenting solutions to some of the most pressing global challenges in an accessible way is highly appreciated. I am Shandilya, Regional Coordinator for EURAXESS Australia and New Zealand. EURAXESS is an initiative of the European Commission that addresses barriers to the mobility of researchers and seeks to enhance scientific collaboration between Europe and the rest of the world. We provide free information about European research, career opportunities, international collaboration, and networking possibilities. These are exciting times for international research collaboration, as last week we did the official launch of Horizon Europe in Australia and New Zealand. Horizon Europe is the European Union's key funding program for research and innovation, with a budget of 95.5 billion euros for the period of 2021 till 2027. To all those who are watching us, if you are interested in European funding as a researcher, or if your institution would want to work on projects in collaboration with European Research Organization, get in touch with us. Consistently to our philosophy of reducing barriers to scientific collaboration, we have decided on a long-term partnership with the Australian Academy of Science and the Embassy of Germany in Canberra to be involved with Falling Walls Lab in Australia. As a new initiative, we were also very happy to organize the first ever state heat of Falling Walls Lab in New South Wales, taking applications from NSW, ACT and Tasmania. It would have been very logical for EURAXESS to offer today's winners a trip to Europe to visit a laboratory of their choice, as we have done in other parts of the world in the past with Falling Walls Lab. But with the current COVID-induced circumstances, we will invite the winners to do a virtual course in scientific communication with European trainers, which will help them to prepare for international contest in Berlin. In addition, we will also facilitate connections desired by the winners in Europe should they want to establish contacts, and this could be liaising with research organizations in the field, connecting with any of the 600 plus EURAXESS centers in Europe, or introduction to prestigious European Research Council grantees or Marie Sklodowska-Curie fellows. I leave you with a famous quote from Marie Sklodowska-Curie herself: "Nothing in life is to be feared, it is only to be understood. Now is the time to understand more so that we may fear less." Good luck to all of you, and thank you very much.
Well, that's absolutely fantastic. Yes, and I want to thank John and Nishat very much. I'm taking over from Hans, as we've seemed to have some unfixable technical problems, but we've hung in there nevertheless. And it's wonderful to have EURAXESS as a partner, and we look forward to continuing that relationship into the future. So now what everyone's been waiting for is the announcing of the winners. So let's quickly recap our 10 presenters. There's 9, but anyway, let's go. So first one is Elizabeth. Bring the slide up. The first one is Elizabeth Austin from Macquarie University. Then we have Saffron Bryant from RMIT University. Lars Esser from CSIRO. Arinze Ezieke from the University of Queensland. Sara from the University of Queensland as well. Jiao Jiao Li from the University of Technology, Sydney. And Chamikara Liyanage from Queensland University of Technology. Lokman Norazmi from the University of Tasmania. And Anushi from the Murdoch Children's Research Institute. So look, thank you and congratulations to all of you. Your presentations were just fantastic. So I now get the chance to announce the People's Choice winner. And according to the votes from the audience, we actually have a tie. So the winners are Lokman Norazmi and Chamikara Liyanage. So congratulations to both of you. And I want to invite you both to say very few words. So let's start with Lokman. Over to you. I think you might be on mute.
I would like to thank everyone for the support, especially my research team, my family, and also to the Academy for giving me this opportunity. Thank you.
And Chamikara.
Thank you so much for my research group and my supervisors and my family back in there. And I would like to thank all the organizers and the Australian Academy of Science for organizing this. Looking forward to it.
So look, thank you so much and congratulations. So I'd also like to congratulate everyone who's been on the event today and all the hard work that goes in preparing a presentation. I know doing a talk in 3 minutes is probably even harder than giving a full hour lecture. So I now have the pleasure of announcing the official winners of the Falling Walls Lab Australia 2021. And they will be representing Australia at the Falling Walls International events in November. I have to say it wasn't an easy task, and all of you would have been absolutely fantastic representatives on behalf of Australia. But the jury has come to a decision, and so I'm going to go backwards from third place to first place. So now I'm thrilled to announce third place is awarded to Lokman Norazmi. So Lokman, congratulations. And would you like to say another few words on congratulations on being third place?
Again, thank you so much to everyone. Thank you to my friends, my family, and of course my research team. This is our work. It's not just me alone. And I look forward on representing Australia. And again, thank you to the Academy, EURAXESS, and everyone. Thank you.
That's brilliant, and congratulations. So now the next one is our second place award, and this goes to Chamikara Liyanage, and over to you, Chamikara. Congratulations.
Yeah, thank you so much. I would like to thank my supervisors and my research group and my family back in there in Sri Lanka. And I would like to thank all the people who initiated the research and with groundbreaking results. I hope to break through major walls in the science in next few years, and I hope to make proud Australia in next rounds.
Well, thank you so much, and congratulations, Chamikara. So now, finally, our first place winner, and this is awarded to Jiao Jiao Li. So congratulations. And I have to say that one of the judges said, you never hear stem cells and machine learning in the same sentence very often. So over to you. We'd love to hear from you and a few words from you, Jiao Jiao.
Thank you so much. I was not expecting this result, but I'm very glad to be progressing with this innovative research as the jury has decided. And thank you so much to everyone who's tuned in to listen to my talk today. Thank you to my supervisor, to my peers, and to my family and friends. Thank you so much. And I look forward to representing Australia. Thank you.
And Jiao Jiao, you'll do a marvellous job. I know that for sure. Your presentation plus also your answers were superb. So look, well done and congratulations all of you who presented, and a special congratulations to our winners. So now I just want to thank, as we close up, our jury. So I was very grateful to have such a great jury helping me with selecting the winners. So I go and point to Dr. Dan Grant, Kate Hart, Rosie Hicks, Professor Michael Schurtz, Professor John Shine, and Dr. Jack Skidil. I'd also like to thank the event, all our partners and donors, both locally and globally, and their contributions have made the Falling Walls Lab possible. We would also encourage everyone to take part in the Berlin events this year because we all can. There's no flights to Berlin required, so this is a chance for everyone to have a go and be present. And the Academy team will share details with those who are registered for today's events and in our social media channels as well. So I hope you'll all tune in November. I know I will. And this concludes the Falling Walls Lab Australia for 2021 event. And it's great to have been here. And as Australia's Chief Scientist, it's been wonderful to see what wonderful and fantastic careers ahead for all these finalists who are going to be our leaders of the future. So well done and bye everyone. And we'll look forward to you joining us again next year.